Okay, so now that we found the eigenvalues of the Gramian of our original matrix, we can proceed to step 2 of our algorithm for calculating the singular value decomposition. And in step 2, we need to factor the Gramian of our original matrix according to the spectral theorem, which means we want A star A equals V times D times V conjugate transpose. And here, D will be the matrix that's diagonal and organizes the two eigenvalues. So D is actually simple to calculate here. D will end up being the diagonal matrix whose diagonal entries are 10 and 4, because 10 and 4 are the two eigenvalues we calculated in step 1. And then the bulk of our work in this video will be devoted to calculating V. Here, the data in V, or at least the data in the columns of V, is the data of bases for the eigenspaces. So the columns form bases of the eigenspaces. So let's go ahead and find bases for the eigenspaces of this Gramian. And since there are two positive eigenvalues here, we're only finding bases for those two eigenspaces. So let's start with lambda 1 equals 10. So the eigenspace of our Gramian matrix, A star A, for the eigenvalue lambda 1 equals 10, is defined as the null space of our matrix A star A minus 10 times the 3 by 3 identity matrix. So we're looking at the null space of the matrix obtained by taking our Gramian and subtracting the number 10 from the diagonal. So the original diagonal here is 6, 4, 4. So the new diagonal will be 6 minus 10, which is negative 4, 4 minus 10, which is negative 6, and then 4 minus 10, which is negative 6. And then all of the other entries are the same. Negative 2, negative 2, negative 2, 4, and then negative 2, 4. Great. So now we want to find a basis for this eigenspace. And the basis for this eigenspace is simply the null space of this matrix. So all we need to do is find a basis of the null space of this matrix. Now, we've been working with null spaces for a while now. So as you know, there are lots of ways to do this. One way to do it is to just eyeball it. The advantage to eyeballing it is that is very quick, but the disadvantage is that it's not always easy. So by eyeballing it, I mean, let's ask ourselves, is there a simple way to take a linear combination of the columns of this matrix to produce the zero vector? And I think if we stare hard enough at this one, I think we might be able to see such a linear combination. If we look at the second two columns, we find here that if we add them together, we get the first column exactly. So negative 2 plus negative 2 is negative 4. Negative 6 plus 4 is negative 2. And 4 plus negative 6 is negative 2. So that gives me immediately a linear combination of the columns that produces the zero vector. If I take 1 times the first column, minus 1 times the second column, minus 1 times the third column, I get the zero vector. So this tells me that a basis vector of this eigenspace is given by 1, negative 1, negative 1. And I know that this is the only basis vector I need because our Gramian here is a rank 2 matrix, which means its null space has dimension 1. Great. So that's our first basis vector of our first eigenspace. Let's look at our second eigenspace. The second eigenspace, so script E sub A star A, the second eigenspace has lambda equal to 4. So now we're looking at the null space of Gramian minus 4 times the 3 by 3 identity matrix, which is the original Gramian matrix and then we subtract 4 from each diagonal entry. So we're looking at the null space of 6 minus 4 is 2, 4 minus 4 is 0, and 4 minus 4 is 0, so we get some zeros in this thing, and then every other entry is the same, negative 2, negative 2, negative 2, 4, negative 2, 4. So now we want a basis of the null space of this matrix. And again, if we can manage to find a vector or a basis vector by eyeballing it, that's great. If not, we can try to do a few row reductions to see if we can't figure it out. Let's see here. Can we find one? What happens if we add the second two columns together? It looks like we get negative 2 plus negative 2, which is negative 4. Then we get 4 and 4. So we get negative 4, 4, 4, which is exactly equal to negative 2 times the first column. So that does give us a linear combination. Here we end up looking at the span of, so what did we say? If we added the second two columns, we get negative 2 times the first, which is to say, if I multiply the first column by 2 and then added the second two columns, I would get 0. So that gives me bases for my two eigenspaces. And this is now enough data to calculate our desired factorization in this step. So we need to find the columns of V here, and the columns of V need to form orthonormal bases for the two eigenspaces. And if we look at the bases for our eigenspaces, we find that they are not orthonormal, so we need to apply the Gram-Schmidt algorithm. And lucky for us in this example, each of these eigenspaces has dimension 1, so Gram-Schmidt, when there's one vector, is just the same thing as normalizing that vector. If there were more vectors in either one of these bases for the eigenspaces, we would have to apply more steps of the Gram-Schmidt process, which is really where most of the tedium in this example would come from. I guess that and the characteristic polynomial calculation. So let's wrap this video up by actually writing down the explicit factorization. So here we have our factorization. The Gramian of our original matrix now factors as V times D times V conjugate transpose. Let's fill in the missing entries of V. So our first diagonal entry of D is 10, because that's the first eigenvalue. So we need the first column of V to be a normalized eigenvector. So here we're looking at 1, negative 1, negative 1. The length of this vector is root 3, so we divide 1, negative 1, negative 1 by root 3. So we get 1 over root 3, negative 1 over root 3, negative 1 over root 3. And then for our second column here, we want the normalization of our second eigenvector, which corresponds to lambda equal to 4. So the length of 2, 1, 1 is root 4 plus 1 plus 1, so that's root 6. So we're looking at 2 over root 6, 1 over root 6, and then 1 over root 6. And then now we have our diagonal matrix D, so the only thing left to do is write down V conjugate transpose just to make this factorization explicit. So all we're doing here is transposing V, since all these numbers are real numbers. So we get 1 over root 3, negative 1 over root 3, negative 1 over root 3, and then 2 over root 6, 1 over root 6, 1 over root 6. So that concludes the second step of our quest for calculating the singular value decomposition of our original matrix A. In step 1, we found the positive eigenvalues of the Gramian, and then now in step 2, we've taken those eigenvalues, found bases for each of the two eigenspaces, and then applied the Gram-Schmidt procedure to each one of these two bases to produce a factorization. A star A equals a matrix V with orthonormal columns times a diagonal matrix D times the conjugate transpose of V.